Thank you for the introduction, and thanks to organizers for this kind invitation. It's a real pleasure to give a talk in this seminar. And tech-wise, I'm not very talented, so I hope my connection does not break down in the middle of the talk. Okay, so I'm going to talk about solutions of a family of equations of active scalars, a family of active scalars that are driven by an incompressible fluid. And these solutions have the property that they lose regularity instantly. But they exist in a bigger space for a long time, and these solutions are unique. Okay. So the family of equations I'm going to study here is the generalized SQG equations. So we have a parameter which is alpha, and alpha goes from 0 to 2. And we have we are in the plane, okay? And so the entire talk is going to be in 2 dimensions. We have the unknown. Unknown is the active scalar. It's a function, and it's theta, denoted by theta. And this theta, this function, is transported by a fluid, a velocity, which is u, and this velocity is divergence free. So therefore, we can define a stream function and take the velocity to be the gradient perpendicular of the stream function. Our solutions are going to decay at infinity. So in order to preserve the energy, or to have finite energy. And by energy, I mean the L2 norm of the velocity. So, and then the relation between this scalar theta with the stream function is given by this power of the Laplacian in terms of the parameter alpha. So it's the Laplacian to the power 1 minus alpha over 2. So this is the system I'm going to study. So for alpha equal to 0, we recover the well-known 2D incompressible Euler equations, where theta plays the role of the vorticity. And the vorticity is the curl of the velocity, which in 2 dimensions means is the Laplacian of the stream function. When alpha is equal to 1, then we recover the equation known as the surface quasi-dystrophic equation. Alpha equal to 1 means that the relation between the function theta and the stream function is given by the square root of the Laplacian. Therefore, one can write the velocity as an integral operator with respect to the theta, and these operators are the Riesz transforms. The Riesz transforms are singular integral operators of a Calderon-Simon type. That means the convolution of a kernel with a function, and this kernel is homogeneous of degree -2. In this case, they're odd, and the mean in the taken of the kernel in the unit circle is 0. So this system actually comes from a geophysical context where it has been used. It's used to understand the formation of fronts of cold air, big fronts made of big masses of cold air with hot air. And this is known in physics as frontogenesis. But there was Peter Constantine, Andrew Maida, and Esteban Tabak in 1994 that they realized that this was a very good model, a 2-dimensional model of the incompressible 3D Euler equations, where the gradient perpendicular theta plays the role of the vorticity. So they share many common properties, the 3D Euler equation and SQG, for example, that the energy, the L2 norm of the velocity, is conserved in time. In the case of Euler equations, the vortex lines move with the fluid. In the case of SQG, these are the level sets of the temperature theta that move with the fluid. And theorems that you can prove for one equation, you eventually can prove it for the other equation. And local webposes are stated for both in Helder spaces and in Sobolev spaces. And the big open problem is to know if this, once you start with initial data in one of these local webposes spaces, does this solution remain in the space or does it produce a singularity in finite time? And this is an open problem for both systems. And when the parameter alpha is equal to 2, then the nonlinear term disappears, it's 0, and what we have are stationary solutions. And if alpha is bigger than 1, then you have a system of equations more singular than SQG. SQG is more singular than Euler, so as you increase alpha, the system is more singular. So I'm going to divide in two Helder spaces and Sobolev spaces. So for Helder spaces, for alpha equal to 0, and for 2D Euler equations, the local webposes for 3D Euler and 2D Euler, this was done in late 1920s, in the beginning, and then the global webposes in 2D, in 2 dimensions, was done in the beginning of the 1930s. And these are work by Lichtenstein, Wolebner, Helder, and Gunther. In the case of alpha equal to 1, and this was done by Yahong Wu in 2005, where he proved local webposes for SQG, and these are when for CK gamma, okay, and gamma is in between 0 and 1, and not 0 and not 1. Okay, same case for Euler equations. And then Donggo Chai, Peter Constantine, and Yahong Wu extended this result for the range between alphas between 0 and 1. And recently there's a paper by Ambrose and his collaborators where they dropped the requirement, and previous theorems were intersection of the Helder norm with decay at infinity, some LP conservation, so the solutions in NLP, and this active scalar conserve LP norms. So this is used in their proof, but actually this group can drop the requirement of theta being an LP, and you still have local webposes. Okay, and this is true for alphas in between 0 and 1, including 1. If we want to look at the endpoint, so that means gamma is 1, so we are talking about the CK norm, then it's locally webposed when alpha is between 0 and 1. And in the case equal to 0, Euler, you even have global existence. In a recent paper appeared a year ago, Sasha Kiselev and his collaborator, he proved for SQG that the C2 norm, they constructed solutions that initially they are small, and the C2 norm grows exponentially in time, and this is for large times. Okay, and they also did the Helder norm C1 gamma, and they prove also that this norm can grow in time exponentially fast. Okay, and in collaboration with my student Luis Martinez Toroa, who is actually applying for jobs this fall, we posted a paper, but it's actually published this year in 2022, a result of what happens for SQG in the endpoint CK. And we prove that in CK, for K bigger or equal to 2, there is a strong ill-posedness and non-existence.
Sorry, what is K of theta 0 positive? What is K of theta 0?
K of, which one, sorry?
Yes, K of theta 0, yes.
This is a constant. This is a constant that depends on the initial data.
Thank you.
So it grows like exponential to kappa, capital T, and kappa depends on the initial data.
Thank you.
Okay, so by strong ill-posedness, I mean that we construct solutions that initially in CK are small, fix the K, and initially at that norm CK is small, and at a certain time, and you can make that time as close to 0 as you want, your CK norm is as big as you want. These solutions are C infinity. These solutions exist for time as long as you want, and they're unique. Well, of course, they are unique because we are in these solutions, since they're C infinity, we are in the local well-posedness regime. And by non-existence, I mean that you start with an initial data in CK, small, and for T strictly bigger than 0, your solution is not in CK anymore. But your solution exists in certain Sobolev space, which is in the subcritical case, and this solution exists for as long as you want. Okay. Okay, so I will state the theorem precisely later, and I'll give you an idea why this works. So Hilbert spaces for alpha bigger than 1. Well, in that case, Kiselev and He, using same approach, they show that the C1 gamma norm grows also exponentially in time. And this for alphas bigger than 1. There's a relation between gamma and alpha, where gamma has to be strictly bigger than alpha minus 1. And Luis and myself, and this is a paper we posted last July, we show that there is strong ill-posedness for Helder norms, and now Helder norms CK beta, now beta we allow to reach the endpoint. So it goes from 0 to 1, including 1. And these solutions, strong ill-posedness, these are C infinity, and the Helder norm can grow as fast as you want in a time as short as you want. And also we prove non-existence. Initially, your Helder norm is small, and in time t bigger than 0, your Helder norm has diverged. But you still have a solution. The solution is unique, and you're in space and a solid space, and this solution exists for a time as long as big as you want. Okay, now Sobolev spaces, and here's a different story. For Sobolev spaces, there's actually local well-posedness for HS for S bigger than 1 plus alpha. And this is for the entire range of alphas between 0 and 2. And this was a joint work with Don Gochai, Peter Constantin, Francisco Gancedo, and Yahong Wu. Pai and Wu for SQG in the critical Sobolev space H2, they proved that local existence still exists for a logarithmic implicit regularization of SQG. Okay, and this result was extended for all the range of alphas by Joly and their group recently. Kiselev and Nazarov they proved that there exists initial data arbitrarily small in HS. Now S has to be strictly, it has to be bigger than 11, that become large after a long period of time. And the open problem is for the entire range alpha between 0 and 2, not including 0 and not including 2, is there global existence or there's singularities in finite time. Okay, so this is for alpha equal to 0, we have 2D Euler equations, and if we are in the space H1 plus epsilon, then we know that there's global existence. And for alpha strictly bigger than 0, we have no clue. And there are results by Kiselev, Yao Yao, Klatos, and Risnik, where if you have a family alpha close to 0, between 0 and I don't remember exactly, but 1/12, and you have solutions that are patches, and you are in the half plane, then these solutions actually exist for a short time, and they prove that there's a singularity in finite time. But these are solutions with very low regularity. For a higher regularity, it's an open problem, and all the construction we have of instant blow-up or losing regularity instantly, these are a perturbation of a circle. Radial solutions are stationary solutions of this system. So, since their stationary is natural and easier to deal with, is to perturb the radial solution and see what happens. So I'm going to show that we can lose regularity, but let me take a parenthesis and mention the previous work we did where we perturb a radial solution and for SQG, and by perturbing a radial solution, we obtain solutions where there's no growth at all. And these solutions are perturbation of radial. These solutions are C2, and they have some symmetry. They are threefold symmetry. They have threefold symmetry. They're very close to a radius profile. And what these solutions do is that they rotate with a constant velocity, and the shape of these profiles does not change. So the HS norm, the CK norm remains the same. The proof for this result for alpha equal to 1, since it's very singular, it required a computer system proof. But if you look at the case of alpha between 0 and 1, strictly smaller than 1, then one can actually do it by hand. And similar solutions, including for 2D Euler. Okay, this was a small parenthesis, and we're back to constructing loss of smoothness in supercritical and critical spaces. So we are in now solid spaces. Now we are in the critical or supercritical. That means S is smaller or equal to 1 plus alpha. Alpha equal to 0 to the Euler. There is a celebrated work by Bourgain and Lee, and later with a different proof, Elgini and Gion prove similar results, where they prove strong ill-posedness in H1, in the critical space H1, and non-existence of uniformly bounded solutions in H1. A year ago, Kwon following the same strategy they did, she proved that there is still strong ill-posedness in H1 by in H1 for Euler equations, but in a logarithmic regularized version of 2D Euler. Okay. This is in contrast of previous works of Donggochai and Yahong Wu, where they prove local existence for a regularized version of SQD. And a year ago, Jiang constructed solutions for now supercritical norms. These solutions that he constructed are in the Udovich class. That means it's an L infinity intersection with L1. So you know that they exist and they're unique. And these solutions are in W1P, P strictly smaller than 2. And he proved that P is actually a function of time and decreases. So it decreases in a continuously in time. And so it's not that you get a lower, you're losing regularity, but it's in an integrable way. Okay. Now for alpha equal to 1, my work with Luis, we proved strong ill-posedness in the critical space H2 for SQG and non-existence of uniformly bounded solutions in H2. And 2 days after we posted this paper in the archives, Jiong and Kim posted another article. They proved the same thing with a different approach. Our approach gives us more information. We can prove more things. We actually can prove strong ill-posedness and non-existence of solutions for supercritical norms. So if we go to HS for S bigger than 3/2 and smaller than 2, this so we start with an initial data in HS in that range, and instantly afterwards you lose your HS norm, but you remain in H3/2, and the solutions are unique in the space in which these solutions exist. Okay. And this is a result I announced in this for the first time, and this is a paper we posted this month. Is that we studied the case of 2D Euler, and we are in the supercritical regime. Okay, so now critical regime is H1. If so we prove that there exists. Now let me talk about vorticity in this case. So vorticity in H beta initially is smaller than epsilon, small. Beta is any value in between 0 and 1. And then there exists initial data with those properties such that instantly after 0, and the H beta prime blows up, and beta prime is a number smaller than beta, bigger than 0, that satisfies that inequality. Beta prime is any quantity bigger than 2 minus beta times beta divided by 2 minus beta squared. So, and these solutions are not in the Udovich class, but we can prove that they exist. They exist globally in time, and they are unique. And they're unique in a classical way. They satisfy the vorticity equation pointwise for compact domains. Okay. Beta prime, as you can see, the endpoints. And so this means that you have a gap, a loss of regularity, and there's a gap. In compare with Gion's results of the W1P, that you lose regularity in a continuous way. In this case, you have a gap loss of solid regularity. And in the endpoints, you see at 0 and 1, you don't have the gap. And this is a joint work with Luis Martinez-Zoroa and Wojtek Ofensky. Okay, so let's see. Okay. So let me state the result with detail of the Helder strong Ill-posedness in Helder spaces for alphas in between 1 and 2. So this is the strong Ill-posedness result that says that give me beta is any, it can between 0 and 1, including 1. Alpha is the equation, the active scalars in which we are. Delta is a parameter that we need for the proof, and that has to satisfy this inequality in the relation between kappa, beta, delta, and alpha. Then for any capital T measures the existence of these solutions. So we can make this exist as for a time as large as we want. T-crit is the time in which you guarantee that your solution is bigger in the Helder norm, is bigger than 1 over epsilon 2. And you choose epsilon 2, and epsilon 2 can be as small as you want. Then there exists initial data where initially the Helder norm is smaller than epsilon 1, and epsilon 1 can be as small as you want. These solutions are in certain subtle space, but they're actually, this is badly written, they're actually C infinity. Okay, for this theorem, these solutions are C infinity. Then your Helder norm at times T-crit is as big as you want. Okay, so these solutions, they exist for very large times, and the second theorem is non-existence. And in this for this theorem, same betas, same alphas, same deltas, same conditions. You give me a capital T, that's the time of existence of your solutions. You give me an epsilon as small as you want. There exists a function, an initial data, who initially is smaller than epsilon, and for T bigger than 0, up to capital T, these solutions, the Helder norm is infinity, diverges. And now these solutions are not C infinity. These solutions exist in certain subtle space, and the space depends on K, beta, and delta. Okay. Okay, so now I'm going to give you an idea of why this works and what is the strategy of the proof. Okay, so this goes back to the work of Bourget and Lee in 2014 and 2015, where they prove that for Euler equations 2D and 3D, 2D, let's stick with 2D. If the velocity in CK, then you have strong Ill-posedness. Okay. Before it was that the vorticity is in CK, and this is two completely different worlds. If the vorticity is in CK, then you have global existence. But if the velocity is in CK, you have strong Ill-posedness. And even stronger results. The essential supremum of the CK norm blows up. Okay. And And this was also proven by Tarek El-Hindi and Mahmoudi, and later with a different approach. And they also proved this for H1, which I already mentioned before. Okay, so why does this work? Well, one has to write the Euler equations, not in the vorticity form, has to write it in terms of the velocity. So we have the velocity is transported, and the material derivative of the velocity is equal to minus the gradient of the pressure. So we have the pressure. Now we want to write the pressure in terms of the velocity. So we take the divergence of the Euler equations. And we're left with the Laplacian of the pressure equal to the gradient of a combinations of products of the velocity with the derivatives of the velocity. This is something we can invert the Laplacian, and we have the pressure in terms of a product of components of the velocity and its derivatives in the integral form. But now we want to look, what we want to show is that the CK norm, let's say the C1 norm of the velocity, grows very fast. Can we make it grow very fast? So we take the gradient of Euler equations, and that's the equation that appears there below, where we have the gradient of u, the derivative in time of the gradient of u, two terms that are nonlinear, and then and on the right hand side we have the term that comes from the pressure. And what is this? This is a combination of Riesz transforms. So these are singular integral operators with respect to products of derivatives of u. So singular integral operators does not conserve the L infinito norm. So what they do is they cook up an initial data in which the gradient of u is as small as you want, but this singular integral operator is as big as you want.
Sorry, what are I, R, J?
The Riesz transforms. These are singular integral operators in 2 dimensions, the ones I wrote before. Here. These are the Riesz transforms.
Thank you.
Okay, so already you can cook up an initial data where the right-hand side of the equation is as big as you want initially, right? You can even make it infinity. And your solution is in C1. So you're looking at the evolution. So what you have to make sure in your estimates is that the nonlinear terms does not kill this growth. Okay, so let me put a baby model. And this baby model is this 1D linear case. We are in 1 dimension, f is our unknown, we take the derivative with respect to time, we get rid of the nonlinear terms, and that's equal to transform. Hilbert transform is the only singular integral operator in 1 dimension of the Calderon-Singleton type. This equation we can actually integrate, and the solution is written there, f of xt. So at time t equal to 0, the sign is 0, and you have your initial data, which can be as small as you want. But if you cook up an initial data such that the Hilbert transform is unbounded, as time grows, your solution is unbounded. That's the idea. Okay? That's what's behind. But this is not as easy as it sounds, because the nonlinear term can kill the growth. And let's add to this baby model a nonlinear term, a Burger's type. Okay? So we have this equation. This is known as the Burger-Hilbert equation. If the Hilbert transform is not there, then the L infinity norm of f is preserved. Nothing happens. And in our work in collaboration with Ángel Castro and Francisco Gancedo, we proved in 2010, we studied this equation. We were interested because the Hilbert transform, although it's of the same order as the function, it may produce growth. And in this case, what we prove is this inequality pointwise, which means that this inequality is true as long as the function is C1 gamma. And we prove, and if the solution remains C1 gamma, then the L infinity norm of F, and this is due to the Hilbert transform. And we were very excited about this result. But later in 2014, Bersan and Guyen proved that actually there's global existence in L infinity intersection with L2. So the L infinity norm of F is bounded. It's actually, for each initial data, you have a bound. So our pointwise inequality is not wrong. What's happening is that once it reaches the bound that Bersan and Guyen calculated, your solution is not C1 gamma anymore. So there's a blow up on the C1 gamma. Okay. I thought this was very neat, but it gives you an idea that be careful with the nonlinear terms. Okay, so in 2020, and now the question comes to what happens with SQG. Do we have a similar result? And Hindi Mahmoudi made a perturbation of a function that depends only in x2. And if you look at the equation of evolution of this perturbation, it satisfies this equation over here, where you can see that the linear term, because G is given, is the one on the right-hand side has a Riesz transform. R1 is the Riesz transform. And that's a single integral operator, so that is leading to a strong Ill-posedness result. But what they were able to prove what's mild Ill-posedness, is that you can assure that instantly your solution is bigger than a certain constant, C. So this is not strong. Strong will be in the case where C is 1 over epsilon. Then you can make it as big as you want. For example, this does not lead to strong Ill-posedness. If you have strong Ill-posedness, this happens. But if you might have, for example, for SQG, if you look at the Helder norms are locally well-posed. And they satisfy this property. They're mildly Ill-posed in Helder norms. But there's local existence, so therefore there's no strong Ill-posedness. Okay, so this requires a new approach. And this is what we did. So let me, how much time do I have to?
Just 10, 15 minutes.
Okay. I'll make sure that there's no more than that.
No, 15 is okay. Perfect. Thank you.
Okay. So how to prove this for SQG? So let me focus on the CK case. And then I will tell you about the Helder case. So CK for SQG. So first, we're going to prove strong Ill-posedness. Strong Ill-posedness is that there exists, initially your norm is small, and that there exists a T star bigger than 0, where your norm, CK norm, is as big as you want. Okay. So we're going to, we know that radial solutions are stationary. We're going to perturb one of these radial solutions, and this is going to be our initial data. And we're going to construct pseudo solutions. And by the pseudo solution, I mean that it's a solution that satisfies this theta bar, that satisfies SQG with a source term, capital F. Of course, this is not saying anything, but by pseudo solution is that we require this capital F, this source term, small in certain norms, okay? So we're going to construct a pseudo solution. How to do this? So we we have our solution is going to be a radial plus a perturbation. We plug this in SQG equations. So that's exactly what appears when you plug the solution in the equation. And you have one nonlinear term, quadratic term, with the one in the right-hand side. And the rest are linear. So we're going to start with things that are small. Our perturbation is going to be small. Let's get rid of the quadratic term. So now we have this new equation. Now this new equation, F is going to be given. It's our radial initial radial solution, which is stationary, and that's going to be given. So I have freedom to play with my F. So the unknown is theta tilde, pert. Okay, now let's, the second term is just a transport term, right? I'm just taking the derivative with respect to alpha. Now, by the way, I passed from x1, x2 to radial variables, r and alpha. So that's just the transport term. And the third term, we have UR. UR is the radial component of the velocity. The velocity is composed of singular integral operators. So this is a singular integral operator. So I'm going to do the following approximation. I'm going to say that this it approximates to the Hilbert transform, and the Hilbert transform taking in the angular component. I'm going to take also F, where I'm actually measuring that things grow. And I'm going to take my F to be linear in R. So let's take this derivative with respect to R to be a certain constant, C to 0. Now I have this equation. This equation is, I'm going to solve it. And I have these solutions, okay? These are solutions of this equation. They're exact solutions of this equation. G is a function that depends only in R and it's independent of time. And this is something I can cook up from the beginning. And U alpha is the velocity in the angular component of the velocity. F is again my initial radial function, and this is I can cook up as I want it. And capital N is a parameter that I'm going to take it as big as I want. And C sub 0, I'm going to actually take it to be 1. Okay, so this are solutions of this equation, but this equation is linear, so I can add terms of this sort as many as I want. Okay, so this is what I'm going to add K of them, capital K of them. So my solution theta bar is going to be this of this sort. The radial solution is going to be lambda. Lambda is a parameter that I'm going to choose. And actually I'm going to choose it small, but it's a parameter. Capital K is a parameter and capital N is a parameter, which I will choose later. So my solution will consist of lambda times F1 of R. This is my radial, initial radial stationary solution. And then plus lambda times F of 2. This F2 is our G, our previous G. That is radial, but it's going to depend of that form with N, the square root of N, capital N. And then I added the signs up to K times. Okay. This is an expression. Why do I choose this? This is a solution, okay, of my previous approximation. It's an exact solution. At time equal to 0, t equal to 0, this is bounded by a constant which only depends on F1, F2, and this is going to be given, times lambda. So if initially my C2 norm, I'm going to look at the C2 norm. C2 norm, I want it small, I have to make lambda very small. Okay? If I look at the H plus 1/4 norm, this is bounded by lambda, by a constant, times lambda times capital K. So if I already fixed lambda, now I can fix capital K. If capital K is finite, then this norm is bounded. So I'm in a space above H2. And if I look at the C2 norm, how it evolves, I can get a lower bound where it depends on some constant, which is independent of all lambda K and capital N, times lambda square, times the log of capital K and small t. So if you fix lambda and you fix the time which you want your C2 norm to be very big, you just have to take K, capital K, sufficiently big to reach that growth. Now look at the solutions. The solutions are C infinity. So now you understand why we cook up this type of solutions. And that's to fulfill these properties. And all these quantities, these estimates, are independent of capital N. Okay. We plug this in the SQG equation and we have the source term, capital F. And the role of capital N is to make our capital F as small as we want. In order to do that is where we have to choose to pick how F1 and F2 have to look like. And they are radius functions. They are annulus. Okay. They are supported in say if F2 is supported only in one region and F1 is supported in two annulus. Okay. And with certain properties, we can estimate of F1 and F2, we can estimate the norm, the bounds, the norms, L2 norm of F, of the source term, the H3 norm, and the H2 plus 1/4 in terms of capital N. And as you can see, we can make the L2 norm and the H2 plus 1/4 norm as small as we want. And these constants that appear, C, are independent of lambda, capital K, and capital T. So these solutions exist because they're C infinity for as long as we want. Once you fix the time, capital T, you can make this source term as small as you want. So now we look at the evolution of our cellular solution minus a real solution. And when we look at the evolution of this will be capital theta, we obtain estimates on the L2 norm and on the H2 plus 1/4 norm, and they are bounded by those terms that you have over there, which is C times T divided by a power of capital N. So we can make them initially, they have the same initial data, so 0. But as time grows, they separate, but we know we can make sure that they don't separate that too much. So for the time in which we have made these estimates, capital T, we can prove the behavior of the pseudo solution is also shared by the actual solution of SQG. Okay, so therefore, the solution of SQG has to grow, the C2 norm has to grow like lambda squared log of capital K T. Give me the T, give me the lambda to make the initial data small. I can give you a capital K to make this as big as you want. Okay, and that will be the proof for strong Ill-posedness. I just showed you the case of the C2 norm growth, but now you can see it's obvious that if you wants to study a higher derivative, CM, then one has to adjust the pseudo solution with powers of M. So it has the properties, the correct properties, and then one has to look at the 8M plus 1/4 norm, and which you can make as small as you want, and the source term, and that is proof for any CM. That's strong Ill-posedness, and now non-existence. What do? We are going to add, so these F1 and F2 are compactly supported, and they're analogous. So this is a block, right? So we are going to add infinity of these blocks, and we're going to put them at a certain distance. We're going to put them in a distance where their interaction we can control. So they will be separated by sufficiently in a sufficient distance to make sure that we control their interaction. And now in each of them, we have a C2 norm that grows like J for times like 1/J. Okay. And at t equal to 0, the sum will sum to any quantity we want, because we can make it as small as we want. But for t bigger than 0, that means you're putting infinity, so you're taking J to infinity, you have something that blows up instantly in time. And to do this, you just have to do the same thing. You have your pseudo solution, you plug it in an equation, look at the source term, and you make sure that you control all the estimates. Okay. For the Helder norm, okay, so when you make the approximation, then you see the equation in the middle. You do the same thing. Now the quadratic term, you get rid of the quadratic term, but the term that had previously the singular integral operator, which was the velocity in the radial component, now what you have is a fractional derivative of this singular integral operator, and that you approximated by a fractional derivative of the Hilbert transform. Okay, and then you cook out and you do the same strategy. You show that these are pseudo solutions, and once you have a pseudo solution with the growth you want, you add infinite of these blocks, and you have a solution that loses regularity instantly. And let me finish with a comment in Sobolev spaces. So Sobolev spaces is similar approach, but in order to prove non-existence, you're dealing with solutions that have very low regularity. So that is a major problem, and one has to hook up a fixed point argument and show that solutions exist with those low regularity, and that the solution is unique in that space. And that makes the problem much harder, and the proof is more involved. And I think I'll finish here. Thank you.